So in this question, we are given a code and we receive a message. We have to determine if there's an error. If there is an error, we have to locate it. And if there isn't, we have to locate it and fix it. And then using this, we decode the message. So first thing that we have is we have this message here. That's the message that we've received. 0110110. Okay, so now we have to use our locations to decode this. So our locations, HV equals 101, 011, 111, 110, 100, 010, 001. Again, I'm taking these locations, transposing them. Build this matrix, and I'm going to multiply this by my vector 0, 1, 1, 0, 1, 1, 0. And now, when doing the multiplication, you can do modular arithmetic at the beginning or at the end. Remember, it doesn't matter. So let's do the first row. The first row is, I'm going to do the modular arithmetic at the end. So it's going to be 0 plus 0 plus 1 plus 0 plus 1 plus 0 plus 0. So it's 2 mod 2. Then it's going to be 0, 1, 2, still 2, still 2, 3. So 3 mod 2. And then it's going to be 0, 1, 2, 0, or sorry, 2, 2, 2, 2, 2. So 2 mod 2, which equals 0, 1, 0. Thus, an error occurred to the P2 bit. Thus, we do not have an error to fix. Thus, the code is 0, 1, 1, 0. Is right there. B, the message is anybody. So while there was an error, and the error was in the location 6 or the P2 bit, it doesn't need to be fixed because it's just a parity bit. So we get the original message. Okay. Now what we have is we have computing a matrix representation, computing a change of basis matrix, and to compute P. I'm going to leave this as something for you to work through. I think it's a good exercise to work through, but I'm going to leave this as a exercise. Okay. Now we have another linear functional question. This linear functional question, what we're doing is we're telling you what happens to the output, and you want to find f of alpha given alpha equals a, b, c. The idea here is that alpha 1, alpha 2, alpha 3 form a basis. So the vector a, b, c equals x alpha 1 plus y alpha 2 plus z alpha 3. And then f of a, b, c is going to equal x f alpha 1 plus y f alpha 2 plus z f alpha 3. And from here, because we know what f alpha 1 is, f alpha 2 is, and f alpha 3 is, we can solve for what the output is going to be. So f of a, b, c is going to equal 2x plus 2y plus 3z. And now I've got to figure out what x, y, and z are. And to do that, I set up a system and solve. So set up system and solve. Right? And I'm going to leave that as an exercise for you guys to work through. Now, B is a little bit interesting because what we do for B is we're going to actually set up and use the Reese representation theorem that F alpha equals F V of alpha, which equals the inner product of alpha with V. So of alpha 1 with V. And the claim is that this is 0. And F alpha 2 is FV alpha 2 because it's a linear functional over R3, which is the inner product of F alpha 2 with V equaling 0. And this here gives us a linear system. So we get the linear system V equals V1, V2, V3. We have the linear system of alpha 1, given alpha 1 is the vector 1, 1, 0, it's going to be 1 v1 plus 1 v2 plus 0 v3 equals 0. 1 v1 plus or negative 1 v2 plus 0 v3 equals 0. This vector is a solution. That's how I show that my first two vectors are 0. Then what I need to do is I need to make sure that this is not a solution. So what I would do is I would first solve for the solution to this system. Then, so 1 solve, 2 make sure f alpha 3 is not equal to 0. Okay. Now we have here, uh, we have a compute a matrix representation, find the matrix F alpha, and then use it to find the coordinates of Ft for this expression. I think this is a valid exercise for you guys to work through. The one thing I would say is that if, let's say, the matrix is 1, 2, 1, 1, 2, sorry. I think this is a valid exercise for you to work with. Here, what I would say is we could ask you the coordinates, or we could ask you specifically to compute ft of, or f of t. If the coordinates are something like 3, 5, 7, if f of t is 3x1 plus 2yx2, and this is 5x3 and 7x1. Again, these aren't what they're going to be, but if this is my coordinate representation, then what did it imply? Because beta is the standard basis, it's going to imply that f of t of x1, x2, x3, this would equal 3x1 plus 2x2, 5x3, 7x1, because it's the standard basis. If it wasn't the standard basis, what we would do is we would do 3x1 plus 2x2 times whatever the first basis vector is, plus, and then 5x3 times whatever the second basis vector is, plus 7x1 times whatever the third basis vector is. So if beta is not the standard basis, we have a slightly different approach. Then we have the extension questions here. This first extension question is quite challenging. And it kind of goes into 3 steps. First, what we do is we show the addition of 2 vectors with even parity. Will have even parity. Then what we do is we show 0 times even equals even in terms of parity, and 1 times even equals even parity. The third thing that we show is this implies any linear combination will have even parity. Okay. Now this implication of any linear combination having an even parity, what this means is that no vector with odd parity is in the span. Thus, the set is not a spanning set. Therefore, it is not a basis. Now, this is challenging. This is a very challenging question, but that's why it's worth 3 marks. There is potential for questions on the exam to be challenging in this way, but with it showing up, it will be a small portion of the exam. Last, we have this question C2, and this question C2 is very similar to what was on. In fact, it's the exact same thing as what was on the homework assignment. The big thing here is this similarity thing. Well, we're looking at the trace of A, and we want to show that it equals the trace of B. Well, we know that A equals B inverse B, or P inverse BP. So what this means is it's going to equal P inverse B times P, which equals the trace of P times P inverse B by A, which equals the trace of P inverse times B as matrix multiplication is associative, which equals the trace of IB, because P times P inverse is the identity, which equals the trace of B. So similar matrices have the same trace, which is quite interesting. Now, this first example here, the trace of AB versus the trace of BA, what you're going to do is you're going to do the matrix multiplication. And then when we do the matrix multiplication, we figure out what is, you take the sum of the diagonal entries. So if you look at A, B, I, this equals the sum of K equaling 1 to N of A, I, K, B, K, I. And now what I want to do is I want to take the sum of J equaling 1 to N, or I equaling 1 to N of this. So it's the sum of I equaling 1 to N of this expression. Okay. And if we take the sum of I equaling 1 to N of BA, this is going to be the sum of I equaling 1 to N of of B times the sum of K equaling 1 to N of B, I, K, A, K, I. And we have to somehow connect these two, somehow enable to get from one to the other. There's some switching orders. If we switch the order of the sums, which we're allowed to do, and then commute these entries, what we'll notice is we'll notice that they actually are the same. Just here, K's first, here's I first. But let's see what happens. So let's swap our sums. Equal 1 to n of sum of I equal 1 to n of A, K, I, B, I, K. We both swapped our sum and swapped our order. So we did two steps. So technically I should do it in one. But you'll notice here it goes I first, then I, K. I then K, I then K, K then I. And here it goes K then I, K then I then K. So we'll actually have to swap our indices in this proof. Or we'll note that the labeling is arbitrary. The labeling of I and K are arbitrary, and that's how we get equality, which is kind of a fun equality.